IEEE Standard 450 recommends checking pilot cell voltage once a month and all cell voltages at least once per quarter. IEEE stands for the Institute of Electrical and Electronics Engineers. Standards established by the IEEE are completely voluntary, although they're universally accepted and applied. Standard 450 also recommends that cell voltages should be checked with the battery charger in the float charge mode. The voltages are tested using an accurate, calibrated voltmeter, such as this digital volt-o-meter. The volt-o-meter is set to the DC volt position. The meter used here automatically selects the appropriate voltage range. These cells are lead calcium, and on float charge should test at about 2.2 volts. The voltage is read to the hundredths of a volt and recorded. As usual, all required safety precautions should be observed. Since voltage testing involves contacting cell terminals, extra care should be taken to not short across terminals. The recorded cell voltages can be evaluated in several ways to identify possible problems. One way is to identify the highest and lowest cell voltages and determine the difference between them. The difference is compared to high and low cell voltage differences from previous tests. If there's a noticeable increase in the differences, an equalizing charge may be needed to raise the voltage of the weaker cells. Another way to evaluate cell voltages is to determine the average cell voltage. Then each cell voltage is compared to the average. Any cell that's below the average by a specified amount should be noted. The acceptable variation from the average is typically specified by manufacturer or company standards. Here, any cell that's 5/100ths of a volt or more below the average will be noted. A third way to evaluate cell voltages is to compare them to a critical voltage. IEEE Standard 450 states that prolonged operation of cells below 2.13 volts can reduce the life of the cells. IEEE Standard 450 also states that a cell voltage of 2.07 volts or below indicates internal cell problems and that the cell may need to be replaced. Low cell voltages by themselves do not necessarily indicate a problem with the cells. They do indicate that the cells have been insufficiently charged, which can happen for a number of reasons. For example, a low float voltage setting may not provide adequate charging current for slightly weaker but still good cells. Cell voltages can also be low because of higher than normal electrolyte temperatures. Higher temperatures increase the internal discharge of a cell and result in lower cell voltage. Higher than normal temperatures may be caused by internal shorting. If this is the case, the cell should be replaced. But higher cell temperature is often caused by outside sources, such as direct sunlight and space heaters. Steps should be taken to minimize the effect of outside sources. Another cause of low cell voltage may be poor intercell connections. Poor connections increase resistance and reduce current flow in the battery. With reduced current flow, weaker cells may not become fully charged and, as a result, will have lower voltages. The resistance from a poor connection can also cause heating. Excessive heating of high-resistance connections can melt the terminals. In extreme cases, poor connections can cause battery fires. Poor intercell connections are sometimes evident by visible corrosion at the terminals, but a terminal connection can look good and still not be good. One way to check connections is with resistance testing. Connection resistance is commonly measured using a micro-ohmmeter. A recommended practice is to connect one probe of the micro-ohmmeter to the positive terminal of a cell and the other probe to the negative terminal of the adjacent cell. This micro-ohmmeter applies a 25 amp test current across the intercell connector and electronically calculates the resistance. It's a good practice to start taking resistance readings at one end of the battery and work toward the other end. Each micro-ohm resistance reading is recorded. Normal resistances can vary with the size of the battery. According to IEEE Standard 484, A resistance reading for a new installation is suspect if the connection has a resistance that's 10% or 5 microohms higher than the average resistance for each type of connection. An example of a type of connection is all intercell connections. Another type is all inter-tier connections. For existing batteries, a connection is suspect if its resistance is 20% higher than the average that was established when the battery was first installed and tested. Or a connection is suspect if its resistance exceeds a manufacturer or company recommended limit. Intercell connections with unacceptable resistance should be cleaned, tightened, and retested. If the resistance is still unacceptable, the cell might need to be disconnected from the battery so that the connections can be disassembled and given a more thorough cleaning. The term specific gravity for a battery cell refers to the density of the electrolyte in the cell in relation to the density of water. A cell's specific gravity is normally an indication of its state of charge. Specific gravity is measured using an instrument called a hydrometer syringe. When specific gravity is checked, all required safety equipment should be worn, and all required safe working practices should be followed to the letter. To measure cell specific gravity, the syringe nozzle is inserted into the cell. The bulb is squeezed and released to draw a sample into the barrel. Some cells have a sampling tube. If electrolyte is taken from a sampling tube, the first sample is discharged into the vent well. Specific gravity isn't read from the first sample because the electrolyte in the sampling tube doesn't mix with and isn't representative of the rest of the electrolyte in the cell. A second sample is drawn for the specific gravity reading. While a sample is being drawn, the syringe is held vertically so the float doesn't touch the sides of the barrel. Enough electrolyte is drawn to lift the float off the bottom of the barrel, but not so much that the float hits the top of the barrel. If the specific gravity is high, the float will ride high in the sample. If the specific gravity is low, the float will sink lower into the electrolyte. Once the float steadies, the specific gravity is read off the scale at the surface of the electrolyte. The specific gravity reading here is 1.222. This is not necessarily the value that's recorded. Specific gravity is affected by temperature, so the reading may need to be corrected for the temperature of the electrolyte. Electrolyte temperature may be checked using a cell thermometer. Here the cell temperature is 68 degrees Fahrenheit. When electrolyte temperature increases, its specific gravity decreases because warmer liquids are less dense than cooler liquids. When the temperature decreases, the specific gravity increases. The normal or standard reference temperature for electrolyte is 77 degrees Fahrenheit or 25 degrees Celsius. To get an accurate specific gravity reading, the specific gravity is corrected by adding 0.001 to the hydrometer reading for every 3 degrees above 77 degrees Fahrenheit. For every 3 degrees below 77 degrees Fahrenheit, 0.001 is subtracted from the specific gravity reading. Some cell thermometers have a specific gravity correction scale opposite the temperature scale. The correction scale here is marked in thousandths. In this example, the electrolyte temperature is 68 degrees Fahrenheit. The correction factor for this temperature is about -3. So 0.003 is subtracted from the specific gravity reading of 1.222 for a corrected specific gravity of 1.219. This is the value that is recorded for the cell. After the specific gravity reading is taken, the electrolyte is returned to the same cell from which it was taken, and the specific gravity of the next cell can be taken. IEEE Standard 450 recommends checking pilot cell specific gravity once a month, and all cell specific gravities at least once per quarter. Specific gravity should be checked before water is added to a cell, because the water doesn't immediately mix with the electrolyte. Under normal float charge conditions, it may take 6 to 8 weeks for the water and electrolyte to thoroughly mix. In addition, specific gravity readings should not be taken during or immediately after a battery is given an equalizing charge. The reason is that it takes time for the sulfuric acid from the plates to mix with the electrolyte, so the specific gravity will continue to increase for a period of time after the cells have been fully charged. For this reason, specific gravity should not be checked until the battery has been on normal float charge for at least 72 hours after an equalizing charge. After cell specific gravities are corrected for temperature, they can be evaluated in several ways. One way is to identify the highest and lowest cell specific gravities and determine the difference between them. The difference is compared to high and low cell specific gravities from previous tests. A noticeable increase in the differences may mean an equalizing charge is needed to raise the specific gravity of the weaker cells. Specific gravity tests, if done at the right time and when properly corrected for temperature, give a good indication of the state of charge of the cells in a battery. All required safe working practices should be followed to the letter. For example, before beginning your work, remove all metal objects, including rings, metal watch bands, metal necklaces, dangling keys, and any other personal items that could cause a short. Even a single cell, if directly shorted, can melt a ring on a finger. Protective equipment should be worn, including a long-sleeved shirt, an acid-resistant apron, insulated acid-resistant gloves, safety glasses or goggles, a hard hat, and a face shield. Some companies also require the use of acid-resistant sleeve protectors and rubber-soled shoes or a rubber mat on the floor. Also, you must know where the eye wash station is located before you begin working, so you won't have to search for it if you need it. Cells that are cleaned with unauthorized cleaning solutions may exhibit crazing, which is cracks in the cell jar. Crazing results from the chemical reactions of certain cleaning solutions with the cell jar. IEEE Standard 450 also states that a cell voltage of 2.07 volts or below indicates internal cell problems and that the cell may need to be replaced. After cell specific gravities are corrected for temperature, they can be evaluated in several ways. One way is to identify the highest and lowest cell specific gravities and determine the difference between them. The difference is compared to high and low cell specific gravities from previous tests. A noticeable increase in the differences may mean an equalizing charge is needed to raise the specific gravity of the weaker cells.